Welcome to another class of process heat transfer. In this lecture I will talk about the third mode of heat transfer, that is known as radiation. Radiation is the energy emitted by the matter in the form of electromagnetic waves or photons as a result of the changes in electronic configurations of the atoms or molecules. Unlike the conduction and convection process, the transfer of energy by the radiation does not require the presence of any intervening medium. In heat transfer studies, we are interested in thermal radiation, which is the form of radiation emitted by the bodies because of their temperature. It differs from other forms of electromagnetic radiations such as X-rays, gamma rays, microwaves, radio waves, and derivation waves that are not related to the temperature. All the bodies at a temperature above absolute zero emit thermal radiations. Here is the classic example of thermal radiation, which is the transfer of the heat from the sun to the Earth's surface by the radiation process. Thermal radiations can travel as easily through a vacuum as it can through air or water. It is a good thing that it does, otherwise the sun would never be able to warm the Earth's surface. When the thermal radiation falls on the object, some combination of the following three things will happen. The radiation will be absorbed by the surface of the object, causing its temperature to change. Number two, the radiation will be reflected from the surface of the body, causing no temperature change. Number three, the radiation will pass completely through the object, causing no temperature change. Here are some general terminologies related to the radiation heat transfer. The first one is the absorptivity. It is represented by alpha. Absorptivity is a measure of how much of the radiation is absorbed by the body. Number two, reflectivity. It is represented by rho. Reflectivity is a measure of how much is reflected when the radiation falls on a particular object. Number three, transmissivity. It is represented by tau. Transmissivity is a measure of how much radiation will pass through the object. Number four, which is known as emissivity. Emissivity is represented by epsilon, and it is a measure of how much thermal radiation of a body emits to its environment. The details of all the terminologies will be explained in the upcoming lectures. The difference between a black body and a gray body. The terms black body and a gray body are discussed regarding the absorption, emission, or reflection of radiation by different substances. First, a black body is an idealized physical body that is also known as an object that can absorb all the incident electromagnetic radiations. Whereas a gray body is a body or an object that emits radiations at each wavelength in a constant ratio less than the unity to the emitted by the black body at the same temperatures. It means that when we compare a black body with a gray body, so a black body will absorb all the radiations, right, coming at a particular wavelength, while a gray body is a body that can absorb certain radiations while it can emit some a part of that radiations. So the key difference between the black body and a gray body is that the black body is an idealized or ideal physical body, whereas the gray body is a non-ideal physical body of the incident radiations. So the heat transfer by thermal radiation is explained by the Boltzmann law. So the rate of heat transfer is directly proportional to the fourth power of the surface temperature of a particular object, right? So there is a directly proportional relationship between the rate of heat transfer to the fourth power of the temperature of the surface of the body, right? So when we remove or replace the proportionality constant, proportionality constant with this constant, so this is known as sigma, and it has a specific value, and it is also known as Boltzmann constant, and it has a specific value which is mentioned here, 5.67 multiplied 10 raised to the minus 8 watt per meter square per Kelvin to the power 4, right? And it is also directly proportional, the rate of heat transfer is also directly proportional to the surface area. So the maximum rate of radiation that can be emitted from a surface at an absolute temperature, that is Ts, it may be represented by in Kelvin or Rankine scale, is given by the Stephan-Boltzmann law. The idealized surface that emits radiation at the maximum rate is called the black body, and the radiation emitted by the black body is called the black body radiations. So the same Stephan-Boltzmann law can be applied to this black body, right? So this black body has the emissivity equal to 1. It means that it has the maximum emissivity. That means that the black body has the ability to emit all the radiations. So emissivity would be equal to 1, and this law would be applicable, and this law would be reduced to this form. Q is the rate of heat transfer by the thermal radiation, is equal to the Stephan-Boltzmann constant, and the T, the surface temperature, to the raised to the power 4. So if the surface temperature is 400 Kelvin, when we put all the values, the rate of heat transfer by the thermal radiation would be equal to 1452 watt per meter square. This is the specialized form of Stephan-Boltzmann law, and it has a special character that is known as emissivity. So the radiation emitted by the real surfaces is always less than the radiation emitted by the black body at the same temperature, and it is expressed by this law, right? So here we have an additional parameter that is known as emissivity, where the emissivity of the surface, this epsilon, is known as the emissivity of the surface, and the property emissivity, whose value is always in between from 0 to 1, and it is a measure how closely a surface approximately close to the black body. So if the emissivity value is close to 1, it means that the body which is under consideration is near to the black body. So this is the table which basically shows that the different emissivities of materials at a particular temperature known as 300 Kelvin. So aluminium foil has a very small value of emissivity, that is near to the 0.07, whereas the water would have the maximum value of emissivity, which is equal to 1 or near to the 1, which is the 0.96. Another important radiation property of the surface is known as absorptivity, as I have already explained in the previous slide, which is the fraction of radiation energy incident on the surface that is absorbed by the surface. Like emissivity, the value of the absorptivity is always in between the range of 0 to 1. The black body absorbs the entire radiation incident on it. That is, a black body is a perfect absorber. So its value absorptivity would be equal to 1. Here comes the Kirchhoff's law of radiation. So Kirchhoff's law of radiation states that the emissivity and the absorptivity of a surface at a given temperature and a wavelength are equal. So let's try to understand from this diagram. So here is the Q incident, the amount of heat which is basically coming onto the surface. So this is Q incident. A part of this radiation will be absorbed on this by this surface. So the Q absorbed would be equal to the absorptivity multiplied by the Q incident, whereas the part of the radiation will be reflected from the surface. So the Q reflected would be equal to 1 minus absorptivity multiplied by the Q incident. In many practical applications, the surface temperature and the temperature of the source of the incident radiation are of the same order of magnitude, and the average absorptivity of a surface is taken to be equal to its average emissivity. The rate at which the surface absorbs the radiation is determined from the figure, which I have already explained here. And this is the same formula which is written on this diagram. Incident is the rate at which the radiation is incident on the surface, and the absorptivity of the surface. For opaque or the non-transparent surfaces, the portion of the incident radiation not absorbed by the surface is reflected back. So the difference between the rates of radiation emitted by the surface and the radiation absorbed is the net rate of heat transfer. If the rate of radiation absorption is greater than the rate of radiation emission, the surface is said to be the gaining the energy by radiation. Obviously its temperature will be increased. Otherwise the surface is said to be losing energy by the radiation, and ultimately its temperature will be decreased. Let us try to understand the radiation heat transfer between a particular object and the surrounding surface. Let us try to understand this object has the emissivity, that is epsilon, and it has a surface area AS, and its temperature is TS. So the temperature of this object is greater compared to the surrounding surface. This is the surrounding surface which has the temperature T surrounding. T surrounding is less than the surface temperature. So the radiation heat transfer between this object and the surrounding surface would be given by this formula. But keeping in mind that the air is present in between this object and this surrounding surface, so we are neglecting the heat transfer by the presence of air or the movement of air molecules. So for the sake of convenience, so we are neglecting the presence of air at this stage in order to transfer the rate of heat, in order to study the rate of heat transfer between these two objects. This is the first object and the surrounding surface, and it is given by this formula, the Q radiation and the emissivity and the Stephen-Boltzmann constant and the surface area. And this is the fourth power of the temperature difference between the surface of the body and the surrounding surface. This is the temperature difference with the fourth powers, and Ts is this body temperature, body surface temperature, and T surrounding is the surrounding temperature at a particular point. The rate of heat transfer by the radiation process is given by this equation. So here comes, in this special case, the emissivity and the surface area of the surrounding surface do not have any effect on the net radiation heat transfer. So the radiation heat transfer to or from a surface surrounded by the gas such as air occurs parallel to the conduction or convection if there is the bulk motion of the gas. So in the previous slide we have neglected the bulk motion of the gas. So here we are considering the bulk motion of the gas between the surface and the gas. Thus the total heat transfer is determined by the adding the contribution of both heat transfer mechanisms. For simplicity and the convenience, this is often done by defining the combined heat transfer. This is known as H. The combined, that includes the effects of both convection and the radiation. So the heat transfer between this object and this surrounding surface occur due to two modes. The first one due to the radiations. The second one is known as by the movement of the air molecules. So the air molecules will move from this place to this place, and the heat will be transferred by the convection process. And the overall heat transfer coefficient would be represented by the combined heat transfer coefficient, that includes the combined effect of convection as well as the radiation. So here is the formula between the two surface, the heat transfer between the two surface surface temperature, and the T infinity is the surrounding temperature. So this H will be known as the combined heat transfer. So the total heat transfer rate to or from a surface by the convection and the radiation process is expressed by this formula. So let's talk about the example related to the radiation process. So the radiation effect on a thermal comfort. It is a common experience to feel chilly in winter and warm in summer in our homes, even when the thermostat setting is kept the same. This is due to so-called the radiation effect, resulting from the radiation heat exchange between our bodies and the surrounding surfaces of the walls and the ceilings. So here comes an example. Consider a person standing in a room maintained at the temperature of 22 degrees centigrade at all times. The inner surfaces of the walls, floors, and the ceiling of the house are observed to be at an average temperature of 10 degrees centigrade in winter and 25 degrees centigrade in summer. So one thing that is very important, that two temperatures are given. So one is for the winter and the second is one for the summer. So determine the rate of radiation heat transfer between this person and the surrounding surfaces if it is exposed surface area and the average outer surface of temperature of the person is 1.4 meter square is the outer surface area of this person, and 30 degrees centigrade is the temperature of this person respectively. So here we have two things that we have to determine. The first one is we have to determine the radiation heat transfer between this person and the surrounding temperatures, between this temperature, between this person and the surrounding walls or ceiling or etc. This person has a particular temperature that is 30 degrees centigrade and it has a surface area of 1.4 meter square, and the surrounding temperatures are two different seasons. The one is in the winter and the second is second is for the summer. For the winter there is a 10 degrees centigrade, and for the summer, for the winter there is a 10 degrees centigrade, and for the summer there is 25 degrees centigrade temperature. Now let's move to the solution of this example. So the solution is the rates of radiation heat transfer between a particular person and the surrounding surfaces at a specified temperature are to be determined in summer as well as in the winter. So you have to determine two different radiation heat transfer. The one is in the summer and the second one is in the winter. So assumptions: the steady state operating conditions exist. Second assumption is the heat transfer by the convection is not considered, because there is always the air between the person and the surrounding surfaces, so the heat might be transferred by the convection process. So for the time being we are just focusing on the radiation heat transfer, so that's why we just keep it neglected, or we do not consider the convection heat transfer. So the third assumption is the person is completely surrounded by the interior surrounding surfaces of the room. The fourth one is the surrounding surfaces are at a uniform temperature. It means that the surrounding surfaces, walls or ceiling or the floor, and the temperature is not changing with the passage of time. They are at a constant temperature either in summer or in winter. So the properties that you need is the emissivity of that particular person, and it can be taken from the table, that is equivalent to 0.95. So here comes the formula that we have studied in the previous slides. So the radiation heat transfer between the two surfaces can be determined by this formula: emissivity, that is given in the table 0.95, and Stephen Boltzmann constant, its value is given and it's constant, and AS is the surface area. AS is the surface area of the body, and TS is the surface temperature of the body, and T is the surrounding temperature in winter. By putting all the values you will get 152 watt, the rate of heat transfer. And similarly for the summer, the radiation heat transfer can be calculated by using the similar formula, but you have to put different temperature for the summer. Keep in mind that the temperatures are given in degree centigrade and you have to put the temperature in Kelvin scale. What you have to do is in order to convert the temperature from centigrade to Kelvin, you have to add 273 degrees centigrade in each temperature. So the radiation heat transfer in the summer would be equal to 40.9 watt. One-dimensional heat conduction equation. So in this topic we will try to understand the conduction of heat transfer in one dimension. So first of all, the heat conduction equation in a large plane wall. We will try to develop an equation for the conduction process in one dimension through a particular large plane wall. So consider the heat conduction through a large plane wall, such as the wall of a house or a glass of a single pane window, the metal plate at the bottom of the pressing room, or the cast iron steam pipe, or the cylindrical nuclear fuel element, or the electrical resistance wire that is being heated or quenched. Heat conduction in these and many other geometries can be approximated as being one-dimensional, since the heat conduction through these geometries will be dominant in one direction and negligible in other directions.
Below, we will discuss and develop the one-dimensional heat conduction equation in a rectangular geometry. So consider we have a thin element here. We have a thin element here whose thickness is delta x in a large plane wall as shown in this diagram. Assume the density of this wall, this thin wall is rho, and the specific heat is C, and the area of the wall normal to the direction of the heat transfer is A. The energy balance on this thin element during the small time interval t can be expressed in the upcoming slide. So this is a cubic element, right? It has 3 dimensions, right? Let's suppose this is the x direction, and we are considering that the heat is being transferred in the x direction only. So we are considering the heat conduction in a large plane wall in 1 dimension. So the heat is being conducted in this direction. So this is qx, right? And this is qx plus delta x. So this point on the left hand side on this wall, the distance is x, and at this point there is some additional distance, so this distance would be known as x plus delta x, right? So the area which is perpendicular to the direction of this heat flow would be known as A, right? And this G is the rate of heat generation, and this is the wall which is under consideration for the development of one-dimensional heat conduction equation. Let us try to understand, or let us try to put the energy balance on this thin element that we have seen in the previous slide. So the rate of heat conduction at the place x minus the rate of heat conduction at the place x plus delta x. So it is in a similar way, heat in minus heat out. So the rate of heat conduction at x, it means that the amount of heat which is basically going in of that thin element minus the rate of the amount of heat which is basically going out of that particular element, plus the rate of heat generation inside the element. So for the sake of convenience, we will neglect this parameter or this part because there is no heat generation. So that would be equal to the net rate of heat, the rate of change of energy content of the element. So this is the general energy balance equation. We can convert it into this form: qx minus qx plus delta x plus G element, which is the amount of heat which is basically generated, and this is the delta E, the change in energy of that particular element with the passage of this time, right? Delta T during the interval time delta T. So but the change in energy content of the element at the rate of heat generation within the element can be expressed as this. So these two terminologies can be explained here. So delta E is the element, that is the net rate of change of energy within the element. So it can be expressed as in terms of time, right? So this is the energy change, right? And energy difference at time t, or t plus delta t, right? So it can be expressed as mc delta t, right? mc delta t. So this c m could be replaced with the density and the area multiplied by the delta x length. So this delta x and A would be simply known as the volume. Volume multiplied by density would be equal to mass. So this mass is translated into density multiplied by the volume, and volume is further expanded into area into length, delta x, and this C is known as the specific heat. This is the delta E. Similarly, this capital G dot element, this is the heat rate of heat generation multiplied by the rate of heat generation multiplied by the overall volume of the element. This volume of the element can be can be opened in the form of area multiplied by the linear length. So the previous two steps can be substituted into this equation in number 2.6, and we will have this equation. So in this equation we will have a delta x and a delta x on the left hand side and the right hand side. So what we will do is we will divide the whole equation with the a delta x. So when we divide the whole equation by a delta x, so a delta x from this part and this part will be cancelled out, and a delta x will be will come here in the division. So this part is qx minus qx plus delta x. So in the mathematical form we always represent that the final minus initial when we try to solve it in mathematical terms. So the final minus initial when we rearrange this part, right? So it will become q delta x, qx plus delta x minus qx. So here becomes the negative sign which will come outside, right? So the simplification of the equation will become in the form of the equation 2.10. When we take the limit of the previous equation on both sides, when delta x approaches to 0, right, means that the very thin element that we are considering for the development of the one-dimensional heat conduction equation, and the time is very small, so the above equation is reduced to this form. And this how this equation is developed, right, and how this part is developed, right, and here is the explanation. So when we take the limit delta x approaches to 0, so according to the definition of the derivative, so it can be written as delta q by delta x. So we know that q is the Fourier's law of heat conduction. So delta by delta x will be written outside, and q can be expanded from the Fourier's law of heat conduction. So it is minus ka delta T by delta x. So this part would be equal to this part, and here this is the simplification of this equation. So noting that the area A is constant for a plane wall, and the one-dimensional transient heat conduction equation in a plane wall becomes just like this one. This is the final equation, and what this equation is saying that the temperature is a function of two different variables, right? So temperature is changing in the x direction, right? This part, right? This part, temperature is changing in the x direction, as well as the temperature is changing with respect to the time. So anything is changing with respect to time is in the conduction process is known as the transient heat conduction. So this G dot is the heat generation element. So this is the final equation of the one-dimensional heat conduction equation. Why we say it is one-dimensional heat conduction? Because it is just saying that the heat is being conducted only in the x direction. So we can take this thermal conductivity outside, but we are considering that it is dependent on material, and it is also dependent on the temperature, so we are taking it as a variable conductivity. So by taking the variable conductivity, so the one-dimensional heat conduction equation would be written as in this way. So if the above equation can be modified based on the assumption that the thermal conductivity is constant, so the above equation can just be simplified in this equation, that is 2.14. So here that is known as the additional property that is known as thermal diffusivity, and it is also the ratio of thermal conductivity divided by the density and the specific heat, right? So this is the rate of heat conduction through a plane wall in one dimension. So the above equation, this equation can be classified into three different cases, right? So first one is if we say that if the process is steady state. What does it mean? That there is no change of anything with respect to the time. So that means that anything with respect to the change in time would be equal to 0. So the right hand side would be equal to 0. This is the equation that describes the rate of heat conduction through a plane wall in one dimension and steady state condition, right? The second is the transient no heat generation. If we say that the condition is transient, what does it mean? That the temperature is changing with respect to the time, but there is no heat generation inside the element that we are considering. So G would be equal to 0 in this equation, right? And the whole equation becomes equal to, in this way, 2.16. And the third is the most important thing is steady state and the no heat generation. So if the process is steady state, it means that there is no change with respect to the time, so this part would be equal to 0. And if there is no heat generation, so this part would be equal to 0. So the steady state heat conduction for this in one dimension through a plane wall would be represented by this equation, that is d square T over dx square is equal to 0. So one thing that is very important to understand, that in these two equations we just mentioned that in this equation we just mentioned the delta sign, right? And in this equation I have just mentioned the d sign. What does it mean? So it means that when a particular independent variable is dependent on two variables, so we always mention this delta sign. So here T is the independent variable and it is dependent on two variables, that is the dimension, that is the direction x, and it is also dependent on temperature time. So that's why the one single independent variable is dependent on two independent variables. So we can write this differential equation in delta form. So in equation 1 and in equation 2, so we can see that the temperature, which is the dependent variable, and it is only dependent on one variable, that is x, right? So we can just write d derivative instead of differential in equation 1 and equation 3. In this topic, let us try to understand the steady heat conduction in plane walls. First of all, try to understand the process, or try to understand this diagram, that this is a rectangular plane wall, and the one side of the wall has a temperature of 20 degrees centigrade and the other side of the wall has a temperature of 3 degrees centigrade, and in between the wall that has a temperature of 11 degrees centigrade. Obviously the heat will be transferred, or heat will be conducted from the higher temperature to the lower temperature. So the direction of the heat would be from 20 degrees centigrade to 3 degrees centigrade. So we have to select the center or the origin that we can put the energy balance on this particular wall. So we have selected this point as our reference point. So we have said that this is x direction, this is y direction, and this is z direction. So let us just try to put the energy balance. So noting that the heat transfer is the only energy interaction involved in this case, and no heat generation. So in the previous slide we have seen that there is the energy generation element. So in this case we are considering that there is no energy generation, so this no heat generation would be neglected. So the simplest energy balance would be written as in this way: the rate of heat transfer into the wall minus the rate of heat transfer out of the wall is equal to the rate of change of energy of the wall with respect to the time. So this can be written as into this form: Q in minus Q out is equal to D, the change in energy of the wall with respect to the time. So the further explanation says that if we consider that the steady state operation, what does it mean? That there is no change of energy, the rate of heat conduction with respect to the time. So this term would be equal to 0 for the steady state operation, since there is no change in the temperature of the wall with time at any point. So we will say that this is the steady state process. So therefore the rate of heat transfer into the wall must be equal to the rate of transfer out of it. In other words, the rate of heat transfer through the wall must be constant. Q dot or the Q conduction will be constant. So consider a plane wall of thickness L, that is from 0 to L, and the average thermal conductivity of this wall is K, and the two surfaces of the wall are maintained at the temperature of T1, and the one side of the wall of the temperature has T1 temperature, and the other side is of the wall has a temperature of T2. So what will happen, the heat will be conducted through the wall from higher temperature to the lower temperature. So we will put we'll have to develop the equation, the heat conduction equation through the wall, and we will consider that this small element through which we can apply our balance, right? So this dx is the thickness of our element which is under consideration, and the temperature change in this element would be known as dt. So the rate of heat conduction through this wall can be represented by this equation. The rate of heat conduction through the wall is equal to minus Ka delta T by delta X, and it is exactly the Fourier's law of heat conduction that we have studied in the previous. So the above equation can be solved, right? So we have the boundary conditions, right? So we have the thickness from 0 to L, right? And we have a temperature from T1 to T2. So the separating the variables in the above equation, so we have the boundary conditions, right? So T0 is equal to T1. What does it mean? T0 means the temperature at 0 length. 0 means X is equal to 0. Temperature at 0 length is equal to T1, right? 2XL, right? So the temperature will lead from T1 to T2. So where TL, it means that the temperature at the length L will be equal to T2, right? So the above equation can be rearranged in this form, and we can just apply the integration on both sides with the limits, and we have this final equation, right? If we have this final equation, so we can easily determine the rate of heat conduction through a plane wall. So what we need to do is we must know about the thermal conductivity, the surface area, the one side of the heat, the temperature of the wall, the other side of the temperature of the wall, and the length of the wall. So we can easily determine the rate of heat conduction through the wall. So the rate of heat conduction through a plane wall is proportional to the average thermal conductivity and the wall area and the temperature difference. So the rate of heat conduction through a wall is directly proportional to three things: the thermal conductivity, the surface area, and the temperature difference, and inversely proportional to the thickness of the wall. So the next topic is the thermal resistance concept in the conduction resistance. First of all, try to understand that if the temperature is T1 on one side and the T2 is on the other side, the heat will be transferred from the higher temperature. That is, let's suppose if the T1 is the higher temperature and T2 is the lower temperature, the heat will be conducted from the higher temperature to the lower temperature. So this is the resistance in between the conduction. So the rate of heat transfer would be directly proportional to the temperature difference and inversely proportional to the resistance. So greater the resistance, less will be the heat transferred from T1 to T2, right? Because there is the inverse relationship between the rate of heat transfer and the resistance. So greater the temperature difference between T1 and T2, so greater will be the rate of heat transfer. So the similar concept would be applied on the Fourier's law of heat conduction that we have studied earlier. So the heat conduction equation could be written as the rate of heat conduction is directly proportional to the temperature difference divided by the resistance. So how can we explain this resistance of a particular wall if the conduction is through a particular wall, a rectangular wall? So this resistance or wall would be equal to the length of the wall and the conductivity divided by the conductivity and the area, right? So greater the length of the wall, so greater will be the resistance of the wall. So greater will be the resistance of the wall, so less would be the rate of heat conduction. So the R wall is the thermal resistance of the wall against the heat conduction, or simply the conduction resistance of the wall. Note that the thermal resistance of a medium depends on the geometry and the thermal properties of the medium. Understand the convective resistance. In the previous we have studied about the conductive resistance. In this we will study about the convective resistance. So consider we have a solid block at the temperature of Ts, and the temperature which is far away from the surface is T infinity, which is the less temperature. So Ts is the higher temperature, so the heat will be transferred from the surface temperature, which is the higher temperature, to the lower temperature, that is T infinity. So this is due to the motion of the molecules of the air which is present in between this surface and this higher T infinity temperature. So this transfer of heat is known as the convective heat transfer. So the convective heat transfer coefficient would be represented by H, right? So consider this convective heat transfer from a solid surface that has a surface area A and the temperature Ts to a fluid whose temperature, which is sufficiently far from the surface, is T and T infinity, which is the convective with the convective heat transfer coefficient H. So the Newton's law of heat cooling, which is basically explains the convection heat transfer, is given by this equation. So this equation could be written as in terms of this equation. So this equation is the same equation as we have studied in the previous slide, but instead of conduction we have convection here. So the rate of convective heat transfer is directly proportional to the temperature difference between the surface and the fluid temperature which is far away from the surface, and inversely proportional to the convective heat transfer. So this R resistance by the convective heat transfer would be equal to 1 over HA. So what will happen? So if the surface area would be very high, what will happen? This R will be very low, and if R would be very low, then the convective heat transfer would be very high. So this can be explained by this concept. This is the Ts is the surface temperature of a solid body, and T infinity is the fluid temperature far away from the surface, and the heat will be transferred from Ts to T infinity through the convective heat transfer, and the resistance which basically this faces during the convective heat transfer is known as the convective resistance, and it is equal to 1 over HA. So this is the third kind of resistance, which is known as radiation resistance, and it has a similar ground that we have studied in the conduction resistance and the convective resistance. So this is the Stephan-Boltzmann law, which basically explains the radiation heat transfer between the two surfaces, and this is the radiation heat transfer coefficient, right? And this H radiation heat transfer coefficient and AS could be written in terms of resistance offered by the radiation, right? Which can be explained by. So this is the third kind of resistance, which is known as radiation resistance. When a wall is surrounded by the gas, the radiation effects, which we have ignored so far, so can be significant and may be needed to consider. The rate of radiation heat transfer between a surface of our emissivity and the area AS at a temperature of Ts, and the surrounding surfaces at some average temperature, that is T surrounding, can be expressed by this law. And we have already studied in the previous slide this law, and we have also seen a particular example related to the radiation heat transfer, the amount of heat transferred by the radiation. So on a similar ground, we can just write down the Q radiation would be equal to the temperature difference between the surface and the surrounding temperature divided by the radiation resistance. So this radiation resistance is the reciprocal of H radiation multiplied by the surface area. So keep in mind that this the resistance, radiation resistance, is inversely proportional to the radiation heat transfer coefficient multiplied by the surface area. Combined heat transfer coefficient. First of all, try to understand that we have this solid surface whose temperature is Ts, right? So the temperature which is far away from the surface is either T infinity or T surrounding. So this Ts is at the higher temperature. So heat will be transferred from this solid surface to far away from the surface. So this could be possible by the convective heat transfer and by the radiation heat transfer. So the coefficient which is basically used in the convective heat transfer coefficient is known as H convective heat transfer coefficient, and the coefficient which is basically used in the radiation heat transfer coefficient is known as radiation heat transfer coefficient. So in this case we have seen that the heat is basically transferred by two different modes, and a part of the heat is basically transferring from Ts to T infinity is by the convective heat transfer, and a part of the heat is basically being transferring from Ts to T surrounding by the radiation heat transfer coefficient. So there are two heat transfer coefficients. One is for the convective and the second one is for the radiation heat transfer coefficient. So we can just add both the values, the convective heat transfer coefficient and the radiation heat transfer coefficient, and we will get the combined heat transfer coefficient, and we can use this combined heat transfer coefficient in order to solve the particular problems. So thermal resistance network. Try to understand that we have this wall, right, and one side of the wall has a temperature T1 and the second side of the wall has temperature T2. On the left hand side, which is far away from the surface, on the left hand side we have a temperature T infinity 1, which is the highest temperature, and the left hand side wall temperature is T1, which is slightly less than this T infinity 1. On the right hand side wall temperature is T2, which is far less than the previous temperatures, and the temperature which is far away from the left wall is known as T infinity 2, which is the minimum temperature compared to all other temperatures, right? So there are three kinds of heat transfers, right? From T infinity 1 to T1 there will be the convective heat transfer coefficient or the convective heat transfer, and from T1 to T2 there will be the conduction heat transfer, and from T2 to T infinity 2 there will be again convective heat transfer, right? So the resistance basically the heat transfer during the heat transfer is the resistance that the heat transfer the resistance. So the resistance which is basically offered during the transfer of heat from T infinity to T infinity 1 to T1 is basically known as the R convective, because this is the convective heat transfer phenomena, and the resistance which is basically offered during the heat transfer from T1 to T2 is the R wall, which is the conductive resistance. And again from temperature T2 to T infinity 2, again the phenomena is the convection heat transfer coefficient, convection heat transfer, and the resistance is basically offered by the R convective. So there are three different kinds of resistances if the heat is basically transferred from T infinity 1 to T infinity 2. So there are three different kinds of resistances. So what we have studied in previous slides, that the rate of heat transfer is directly proportional to the temperature difference and inversely proportional to the resistances. So here we have three resistance, so we'll take the sum of all the resistances. R convective 1, so it means that the first the resistance faced during the convection phase, right, and R wall, which is basically the resistance offered by the wall, conductive resistance, and the third one is known as the R convective 2, which is basically offered faced during the second convection heat transfer. So this overall equation will explain that the rate of heat transfer is directly proportional to the temperature difference and inversely proportional to the overall resistances. So this overall resistance will be the sum of three different kinds of resistances.
So in this example, the rate of heat convection into the wall is equal to the rate of heat conduction through the wall is equal to the rate of heat convection out of the wall. So the above part can be expressed in terms of equation, that this is the first part, that is the rate of heat convection into the wall, the second one is the rate of heat conduction through the wall, and the third one is the rate of heat convection from the wall. So after rearranging this equation, we can write the above equation into this form, right? And after further rearrangements, we can have the equation in terms of their thermal resistances. So the first one is the convective resistance, second one is the wall resistance, which is also known as the conductive resistance, and the third one is also known as the convective resistance. So we can add all the resistances, and we can have a cumulative final equation that relates, or that explains the temperature from T infinity 1 to T infinity 2 and the overall resistance T R total, and R total is actually the sum of the convective resistance, conductive resistance and convective resistance at location 2. And this is the practical example in which you can see that the temperature differences between the first mode of heat transfer, the rate of heat convection, is only 20 degrees centigrade, and the temperature difference due to the rate of heat conduction through the wall, right, is the 150 degrees centigrade, and the third part is the rate of heat convection from the wall is only 30 degrees centigrade. So here are the temperature differences in these three modes of heat transfers, and their respective resistances will be 2 degrees centigrade per watt, and 15 degrees centigrade per watt, and 3 degrees centigrade per watt. Here we can see that the temperature drop across a layer is proportional to the thermal resistance. So the maximum temperature drop is in between the conductive resistance. So the maximum resistance that we have face is the conductive resistance. So there is the maximum temperature drop is in between the through the wall, and we have seen the maximum conductive resistance in the wall. So here we have the formula. R total is actually the sum of all three resistances, and these are further can be expressed as in terms of their convective resistances, conductive in terms of convective heat transfer, and the thermal conductivity. We summarize this as the rate of steady heat transfer between two surfaces is equal to the temperature differences divided by the total thermal resistance between two surfaces, and it can also be expressed as delta T is directly proportional to the thermal resistance, which indicates that the temperature drops across n layer is equal to the rate of heat transfer times the thermal resistance, and the mathematical form of this sentence is mentioned here. You may recall that this is also true for the voltage drop across any electrical resistance when the electric current is constant. It is sometimes convenient to express the heat transfer through a medium in an analogous form, or in an analogous manner to the Newton's law of cooling, as Q dot, that the rate of heat transfer, is equal to the U, which is known as the overall heat transfer coefficient, A is the surface area, and delta T is the temperature difference. In this slide you can see that we have two layer plane wall which is subjected to the convection on both of the sides. So the first is the convective heat transfer, and then there will be the conductive heat transfer in the wall 1, and there will be the conductive heat transfer in wall 2, and then at the end there will be the convective heat transfer. So in each of the conductive or the convective heat transfer there will be the certain resistance, and it will be represented by R1 convective and R1 and R2 and R convective 2. And similarly we can write down the overall resistance in this way,
and it is connected with the overall heat transfer coefficient UA. So the overall resistance is inversely proportional to the product of overall heat transfer coefficient and multiplied by the surface area. Now let's talk about an example related to the heat loss through a wall. So let me just read the question statement that consider a 3 meter high and a 5 meter wide and a 0.3 meter thick wall through thermal conductivity is whose thermal conductivity is 0.9 watt per meter per degree centigrade, as you can see in the diagram. On a certain day, the temperature of the inner and the outer surfaces of the walls are measured to be 16 degrees centigrade and 2 degrees centigrade respectively. Now what you have to do is to determine the rate of heat loss through the wall on that day. So as you can see that the one side of the wall is the temperature is 16 degrees centigrade and the other one is the 2 degrees centigrade. Obviously the heat will be transferred from the higher temperature wall to the lower temperature wall, and this is the direction of the heat transfer. So these are the dimensions of the wall, the 0.3 meter thickness and 5 meter wide and the 3 meter high. So here is the solution. So the first thing is the two surfaces of a wall are maintained at a specified temperature. The rate of heat loss through the wall is to be determined. Now we have to take some certain assumptions in order to solve that question. The first one is the heat transfer through the wall is steady since the surface temperature remains constant at a specified values. Number two, the heat transfer is one-dimensional since any significant temperature gradient will exist in the directions from the indoors to the outdoors. Now the number three assumption is the thermal conductivity is also constant. We can have the value of thermal conductivity which is also given in the question statement, that is 0.9 watt per meter per degree centigrade. So the next thing is we have to do the analysis of this question statement which is given in the previous slide, and we can easily calculate the perpendicular surface area to the direction of the heat transfer. So we can just multiply 3 meter into 5 meter and we can have the 15 meter square is the perpendicular surface area, and the steady rate of heat transfer through the wall can be determined in the previous equation. So there is the simplest equation that we have temperature T1 and T2, we have the length that is 0.3 meter, and we have area and we have conductivity. By putting all the values we can have the rate of heat transfer is equal to the 630 watt. There is another way to solve this problem, that we could also determine the steady rate of heat transfer through the wall by making the use of thermal resistance concept, and this is the equation that we have just studied in the previous slide, that the rate of heat transfer is directly proportional to the temperature difference and inversely proportional to the resistance. So in the first step we can determine the wall resistance, and the formula is the length divided by the thermal conductivity multiplied by the surface area. We can just put the values of all the parameters and we can have the wall resistance is equal to the 0.0222 degree centigrade per watt, and after substituting this value into this equation we can have the same answer. 630 watt is the rate of heat transfer through that wall. So this is a problem which we try to solve in two different ways. So there are other problems as well that we can solve in multiple ways. This is another example that is related to the heat loss through a single pane window. So here we have the dimensions of this window that is 0.8 meter high and 1.5 meter wide glass window with a thickness of only 8 millimeter, which will have a thermal conductivity Ka is equal to 0.78 watt per meter per degree centigrade. So first thing you have to determine is the steady rate of heat transfer through the wall, through this glass window, and the temperature of its inner surface for a day during which the room is maintained at 20 degrees centigrade while the temperature of the outdoor is minus 10 degrees centigrade. So this is the window, and the this side, left side, is the inside of the room, which has a temperature of 20 degrees centigrade, and this is the outside of the window that has a temperature of 10 degrees centigrade. So take the heat transfer coefficients on the inner and the outer surfaces of the window, that is, so H1 10 watt per meter square per degree centigrade, and H2 is the 40 watt per meter square per degree centigrade, which includes the effects of radiation. So here we have two different modes of heat transfers, right? The first one is known as the convection, and the second one is known as the conduction. So the temperature decrease from 20 degrees centigrade to T1 is the rate of heat transfer is due to is from 20 degrees centigrade to T1 is due to the convection process, right? And the decrease in temperature from T1 to T2 is actually due to the thermal conduction, right? The rate of heat transfer is due to the thermal the heat transfer through the valve from temperature T1 to T2 is due to the conduction process, and the heat transfer from T2 to minus 10 degrees centigrade is due to the convection process. Here we have three different kinds of resistances. That is the convective resistance from T infinity 1 to T1 degree centigrade, and the conductive resistance due to the glass is from T1 to T2 temperature, and the third resistance is also known as the convective resistance, and that is from temperature T2 to T infinity 2. So we have these three resistances: Ri, which is the inner resistance inside the room, and R glass is the resistance of the glass, which is also known as the conductive resistance. R naught is the convective resistance, which is outside of the room. So the first thing is we have to determine these resistances individually. So the solution is, first we take some assumptions. The heat transfer through the window is steady, and since the surface temperature remains constant, so there will be no transient heat conduction, so it is only the steady state process. The heat transfer through the wall is only the one-dimensional surface, since any significant temperature gradients will exist in the direction from the indoors to the outdoors, so we'll consider it is the one-dimensional heat transfer. And thermal conductivity is constant, which is also given in the question statement of the class, which is 0.78 watt per meter per degree centigrade. So we have to determine, or we have to do the analysis of this question statement. So what we came across is the dimensions of the window. So by using the dimensions, we can determine the surface area of the window, which is equal to the 1.2 meters square. So the next thing is we have to determine the three kinds of resistances: the convective resistance, Ri, which is inside the room; R glass, which is the conductive resistance of the glass; and R naught, which is also the convective resistance for outside the room. So these are the formulas, and we have already gone through all the formulas, and we have all the values, right? So H1 thermal conductivity and H2, these are the values which are given, and we have the surface area just above here. So by putting all the values, we can have all the three resistances. Next step is, so noting all that, the three resistance in series, so we can just add all the resistances, and we have the total resistance for these three resistances. Let's say it will be equal to 0.1127 degrees centigrade per watt, and we can just apply the formula that we have already used for the determination of the rate of heat transfer and between two temperatures. So these are the two temperatures which are given, that the initial temperature is the 20 degrees centigrade, which is inside the room, and the outer outside room temperature, that is only 20 degrees minus 10 degrees centigrade. So by putting all the values and the overall resistance, we can have the overall rate of heat transfer between the two temperatures from 20 degrees centigrade to minus 10 degrees centigrade. And this is the answer of the first part, right? So the second part is you have to determine the T1, which is the temperature of the wall inside the room. So what you have to do is you have to apply the formula, the same formula, and in this formula you have to take the temperature difference of the inside the wall, and you have to put the value of T1, right? And the resistance that you have to use is only the convective resistance, and the Q dot, which is the rate of heat transfer, that you have already determined in the previous step. By putting all the values except T1, you can have the value of the inside wall temperature of the room, which is equivalent to minus 2.2 degrees centigrade. On the similar ground, you can easily calculate the temperature T2, right? You just have to put the temperatures T1 here and T2 here. You have T1, and you will have to put the conductive resistance here. You will get the value of T2 easily.